Have you ever been playing a video game and just marveled at how smooth everything looks? The way the world turns, the way things get bigger as you get closer? You might think it's all just brute force coding, but the real secret, well, it's hidden inside a special kind of number. Today, we're going to pull back the curtain on that secret connection between numbers and motion.
I mean, really think about that for a second. What if you could spin a character on screen without using any complex angles or trigonometry? Just simple multiplication. It sounds kind of like magic, but that's exactly what we're going to break down right now. So, to get our heads around this, we first have to kind of stretch our idea of what a number can even be. We're about to go from a simple, flat line into a whole new plane of possibilities. Right, we all get this. The good old number line. Positive numbers go one way, negative numbers go the other. It's flat, it's one-dimensional. But what if we need to move off the line? What if we wanted to go, say, up? Well, to do that, you need a new kind of number. And here it is. Meet I, the imaginary unit. Now, you probably remember I from math class as that weird thing that equals the square root of -1. But its real power, the thing that makes it so cool, is what it does for geometry. I is the key that lets us literally jump off the number line and into a brand new second dimension.
And when we do that, we get this, the complex plane. Our familiar number line is still there. It's just the horizontal or real axis now. But I gives us that vertical imaginary axis. So a number like a plus bi isn't just a value anymore. It's an actual location, a coordinate at the point a comma b.
Okay, so we've set the stage. We have our new two-dimensional world for numbers. Now let's see the magic that happens when we do something as simple as multiplying by I.
Let's start with something super familiar. The number 3. On our complex plane, it's sitting right where you'd expect, on the real axis at the point 3, 0. Nothing crazy yet.
All right, here's the pivotal question. What happens to that point, to that number, when we multiply it by our new dimensional number, I? The answer is 3i. And just look at what happened on the plane. The point jumped from 3, 0 all the way up to 0, 3 on the imaginary axis. And that is the big reveal. Multiplying by I is the same thing as a 90-degree counterclockwise rotation. It's not just an algebraic rule, it's a geometric action. Okay, if that's true, it should work every time, right? Let's check it. What happens if we take our new number 3i and we multiply it by I again? We get 3i squared. And we all remember that I squared is just -1, so our number is now -3. The point swings from 0, 3 over to -3, 0. It's another perfect 90-degree rotation. Every single time we multiply by I, we just keep turning that point around and around the origin. Okay, so if I all by itself is a pure 90-degree rotation, what happens when we use a full-on complex number? One with both a real part and an imaginary part.
Think of it like a recipe for a transformation. It's not just one instruction. It's two baked into one number. The real part, the a, tells you how much to scale something to make it bigger or smaller. And the imaginary part, the bi, handles the rotation we just saw. Now, these ideas actually have some official math names. The scaling factor is called the modulus. It's really just the number's distance from the center of the plane. You can see from the formula, it's basically just the Pythagorean theorem. That one number tells you exactly how much you're going to stretch or shrink your object.
And in the same way, the angle of rotation is called the argument. It's the angle that the number makes with that positive horizontal axis. That value gives you the exact number of degrees you're going to turn.
And this all boils down to this incredibly elegant rule. When you multiply two complex numbers, you just multiply their sizes, their moduli, to get the new size. And you just add their angles, their arguments, to get the new angle. That's it. That's the whole secret to combining scaling and rotation into one beautiful, simple step. So complex numbers are an amazing way to think about this stuff. But it turns out there's another, even more universal language for talking about these transformations, and that is the language of matrices. Okay, just look at these two things for a second. On the left, you've got complex number multiplication. On the right, you've got a 2x2 matrix acting on a coordinate point. They look completely different, right? But if you actually do the math, they give you the exact same result. That little matrix is just another way of writing down the instructions for a specific rotation and scaling. And this is where matrices really become a superpower.
Instead of transforming just one point, we can take that one single matrix and apply it to every corner of a shape, like this rectangle, all at once. And boom, the entire object scales, rotates, maybe even flips, all in one clean, super efficient operation.
So I know what you might be thinking. This is really cool, but is it just math homework? I mean, why does any of this abstract stuff actually matter out there in the real world?
Well, this quote pretty much says it all. This isn't just a curiosity for mathematicians. The people who build the incredible digital worlds that we all love to play in, they are deeply interested in this exact math.
And it makes perfect sense, right? Every single time you walk closer to an object in a game, it has to get bigger on your screen. That's dilation. Every time you turn your character's head, the entire world has to pivot perfectly with you. That's rotation. Complex numbers and matrices are the computational engine that makes all of that happen smoothly, millions of times a second.
So what started out as this really strange, abstract idea, the square root of -1, turns out to be the foundation of this incredibly powerful system that unifies algebra with geometry. It's a system that powers so much of the modern world, from video game graphics to animation to engineering design.
It just goes to show you, sometimes the most abstract ideas in math have the most powerful, practical applications, hiding right there in plain sight. It kind of makes you wonder, doesn't it? What other simple, beautiful secrets are out there, just waiting to be uncovered?